Hello, today we're going to be talking about equilibrium to expand our knowledge of how to shift a reaction that is at equilibrium to make more of what we would like. In order to do so, we're going to apply the principles that Le Chatellier came up with, and that is that when any system is at equilibrium and it is subjected to a change in either concentration, temperature, volume, or pressure, then the system's going to try and undo that change or readjust itself to counteract the effect applied by the change. And as a result, a new equilibrium will be established. Where this applies is a very common reaction called the Haber process. This is actually the process that results in the Earth being able to sustain as many people as it does, because we can produce ammonia through this process, and we use ammonia in fertilizers. So if your farm or ranch or your garden is requiring fertilizer, it's probably being produced through this Haber process. So we can shift this reaction to make more ammonia in certain ways. For example, if we add more N2, then they're going to collide more often with our hydrogens, and these will react and make our ammonia. As we begin to talk about concentration and how it affects, we're going to shift to another reaction. Our first example is going to involve concentration. To start, concentration will only shift if we're changing an aqueous or gaseous species in a chemical reaction. So in a chemical reaction we'll be using, we have 3 different species, but they are all gases. So adding a gas, either G2B or G2B, will shift our equilibrium. If one of those were a solid, adding that would cause no shift to our equilibrium. The first example we're going to do is shifting by adding more G2. And we're going to take a look in a couple different ways at how this will affect the system. So first, I'm going to add more G2 into my reaction vessel. Now there are more G2s. How is that going to affect my forward and reverse reaction? Because prior, they were equal. We had equal arrows going in both directions. But once we add either a gas or an aqueous from our chemical reaction, it's going to shift it. Well, it would cause the G2 to collide more often with the B's, causing the forward reaction to get stronger. And how we can represent that is I can make my forward arrow longer. Now if I were to add those 2 arrows up, they cancel each other out if they're going in opposite directions. So my overall arrow would be in the forward direction, meaning I'd be making more G2B and using up my G2 and my B in order to do so. As you can see, my stress of adding more is causing it to be used up. Another way of looking at it would be the teeter-totter method. So if I add more G2, it's going to cause that part of my teeter-totter to go down. How do I undo that stress? Well, I'm going to have to make more of the G2B, and then it will level out. So this shift would be a shift to the right. Now what if instead of adding something, we remove something from our vessel? Now we allowed the equilibrium to reestablish itself, and now we're going to cause another stress. In this case, we're going to decrease the concentration of B. So we might remove some of the B's. So I remove one of the B's from the vessel. How is that going to affect our equilibrium? As now our B's have less chance to collide with our G2s, which means that there is a greater chance that our G2B's may break apart. So our forward reaction is actually getting smaller because there was less chance that they collide, meaning that our reverse reaction is stronger, giving our overall reaction, causing it to shift to the left, like so. What does this mean? That our amount of B's and G2s will actually increase, and our amount of G2B's would decrease. How does this look on our teeter-totter method? If I were to remove some B, this side would get lighter. So how do we fix that unbalance? We're going to need to add more to this side. And the only way we can add more within the chemical reaction is that G2B will need to create B and G2. Let's do a practice problem. What would happen to this chemical reaction if we were going to add B? Pause. What do you think? In this case, it would cause it to shift to the right, which would decrease the amount of B we have, but would increase the amount of C. Let's work through another example. In this case, we're going to remove A. What do you think is going to happen? Go ahead and pause to fill in what you think will happen in this case. In this case, it's going to shift to the left, meaning more B is going to be produced by using up some of our C. One last check on learning. What would happen if we added D? Did this one trick you? We got to watch our state of matters closely. D is a solid, and so it would have no shift to our equilibrium.